Good afternoon, everyone. We're going to start our talk about machine learning, classical machine learning, and this is the first session of the series. So I would appreciate if you just do a fast check-in to our workshops. You can just follow that QR code. Okay, and then okay, then okay. I'm going to post the notes on the chat so everyone can have access. So that's the address for the notes. Just GitHub, UV Data Lab /ML Workshops Wiki. Okay. Yeah. So we are good to go. Okay, so is this your first time you are attending a classical machine learning workshop? Are you familiar with what is classical machine learning? Just open your mic and participate. And
Carlos, I've been to the data science workshops before, but I haven't done classical machine learning before, so I'm excited to learn.
okay, thanks. Yeah, it's something that we need to know. Sometimes people ask us that, or you see some paper, some research paper, and they have used specific classical machine learning. And then it's good to know what are our options and how we can do that or do something similar. And in our case, we'll be using Python all the way. So, so when we talk about classical machine learning, we need to know there are several types of learnings, and basically we will have supervised learning, and supervised meaning that the user has to participate, and unsupervised learning means that the algorithm will just try to find all the information um, that that it can do. And then maybe there's a combination like semi-supervised or some other options of interventions in the learning machines, classical machine learning. And so the type of algorithm we will use will depend on what we're trying to do. So for example, if we want to, if you have all your socks in your, after you do your um, laundry, just trying to divide the socks by colors. That's just one sort of classification. So we do this every day. And then, for example, if you want to divide your ties or pants by length, then that's a regression. So we have some length data, and then we can predict some length. Let's say I don't have any tie that measures 8 inches, then you can go and find it. Okay, so under supervised machine learning, we can do classification or we can do regression. Regression meaning you need to find some function or some equation, and then you can mathematically find a number that is not in your data points or your measuring points. And then on the other hand, we have unsupervised machine learning. And let's say you want to divide things by similarity. So for example, you can split your similar clothing into different stacks. So, for example, you can stack all your pants or your shirts, your socks in different clusters. So every element of a cluster has similar properties. So that's called clustering. The other one would be dimension reduction. And so what you will do is try to match outfits from the same clothes. So let's say you select a pants and a shirt. So you're trying to find another way of seeing your problem. And then there is association. And you what you want to do, for example, is find what clothes I often wear together. So you always have a specific number of clothing combinations. So that will be an association. And in classical machine learning, so what we will have is a collection of data sets, and we will use different algorithms for doing the different types of tasks that we want to do. Okay. So here we have the definition for supervised learning. And what I said was the user has to intervene or interact in order to select the appropriate parameters, etc., in order to have the best fit. And for example, we have here an example of a linear regression. So let's say you're doing, let's say you're coming to the university, and then you are just taking notes of how much time it took you to come to the university from your home, and you are also taking notes what time of day you try to travel, and then you will have just a sample of points, and then what you will try to do is find a function. In the first case is the most simplest function is just a linear function. So this data set is gathered in this way. So if I can find a linear function, just a line, that minimizes the sum of the squares of the errors being the distance from the point perpendicularly to the line. And there's a unique line that best fits all your data set. So that would be your best fit. And it has other terms like least square fit, ordinary least square fit. Those are methods that we are used to do in statistics. Or if the data follows some other type of distribution, we can fit another function, which is of higher order compared with the linear. So this can be probably a function that has, this can be a quartic function or some other higher order equation. So these are called linear regression or regression in general. And there are some cases we can do regression. All right. Now, another term is decision trees. So decision trees are used every day for example, will some financial institution give a loan? And the first thing they will ask you, what's your credit history number? If you have a bad credit, then probably say, well, we won't give you a loan. But if the person that is applying has a guarantor, yeah, then probably he can get the loan. If he doesn't have any guarantors, then there's no way the institution will give a loan based on this decision tree. If the person has a good credit history, and then they will ask you how much do you owe. If he owes more than $1,000, then probably you won't get the loan. But if you have a debt less than $1,000, then you will get the loan approved. Okay, so these are called decision trees, and it's just an algorithm. If you have any questions, just interrupt me, please. Okay. Then there are other types of trees. Another one is a random forest. We will see them in detail. Another type of problems we will be working with will be doing support vector machine. So we have several types of drinks, and this is the degree of alcohol of the drinks, and this is the ability to dance better than anyone else. So we have, in this collection, we have beers, and the other set is just wines. And we're trying to find a way to separate both sets. And both sets can be separated in space by this function. In this case, this is a linear function, and we are finding the best separation or the maximum separation between the two sets. And then there are other separation methods or functions, but some functions are not the best fit. And so this will be finding the best fit to separate different elements in space. Can be done using, for example, the support vector machine algorithms. Okay. Then we also have classifiers, naive Bayes. We have the naive Bayes classifier in order to detect if a mail that we are receiving is spam or not. And this algorithm, what it does is just separate or compute the probability of something happening given some previous condition. And at the end, for example, if the contents of the mail message contains, hey, I'm where you speak, learn, etc., those are like good words. But if the contents of the mail message contains the word Viagra, casino, 100% credit, sale, free, etc., then it's probably a spam letter. So this algorithm will just separate between the messages that are not spam compared with those spam letters. And well, we are used to this every day. And we are always asking if some mail message somebody sent us went to the spam or not. Okay. Okay. What about unsupervised learning? And unsupervised learning, for example, we have some set of data or a data set. And the question is this data set, for example, has, let's say we have an Excel spreadsheet, and this spreadsheet has 15 columns. The first question is, are the 15 columns all necessary to understand the problem? So there may be a way that we can find out that probably only 10 of them are relevant to the problem. So instead of working in a space of 15 dimensions with 15 different variables, we can study the same problem in a lower dimensional space of only 12 variables. And these other 12 variables can be constructed for a specific case. And these variables in this lower dimensional space, what we need to do is just to preserve the variability of the data. Okay. So that's principal component analysis. It's just dimension reduction. And there are several methods where you can reduce the dimensions of your problem. Another type of problem are k-means clustering, and we have here an example of how to do. Let's say you're planning to put a kebab kiosk in several places in Tucson, for example. So you just start setting 3 stores or 3 mobile food trucks, and then start measuring how the buyers from the city, from different parts of the city, select which food truck they go. And then what you will try to do is try to find the center of mass of the collection of clients, and put the food truck in the center of mass of that cluster. So you move the food trucks to the center of the mass of each cluster, and then the clients will just try to select the closest food truck to them, and then you continue moving your food trucks until you have these optimal places where people will move the least in order to get to their favorite food. So that's what we call K-means method clustering. And basically, when you have a collection of data points, and then you try to say, well, how many clusters I can construct with this data set. In this case, I'm using 3 clusters, and that's the process of actually defining the 3 clusters. So this data set can be separated in 3 clusters, and these are the center of mass of each cluster. So that's the K-means algorithm, a very basic one. There are other types of separation. One is the latent semantic analysis. So let's say you have a set of documents, and you want to order or cluster or order your documents depending probably, let me, so these are the words. These are the words that are contained in your documents, and you have your documents classified in some way. So we have 17 documents, and let's say document 4, document 10, document 12, and document 16 has the word CrossFit, and document 2, 8, 13, 14, and 15 has the word president. And then we need to find a way, an algorithm, to transform these or find a way of ordering these documents. And these documents can be ordered. For example, all the words that were related with computers can be gathered together or closer. And then all the documents that are health-related topics, then we can form another cluster. And all the other ones that are politically related, then they can be gathered in a different way. So this is a visualization of how to cluster documents by contents, okay, using this single vector domain algorithm. We have other types of clustering, hierarchical, also the Gaussian mixture models, DB-scan, associate rule learning, etc. So these are the types of topics we will be, some of these topics will be viewed in detail with an example. Since this is a workshop, so what we try to do is at the end of each workshop, you should have a Jupyter notebook with some example that you can run or probably adapt to some of your data sets. And then you don't have to know how to program in Python from scratch. The best method that I find is that let's take some code that solves some similar or close by problem that we are interested in solving, and then try to adapt the code. Just, for example, instead of reading the other types of data sets, let's read our data set and then see how well does the algorithm perform. So we will look for different metrics and how to change the different parameters for every algorithm in order to optimize or tune our algorithm in order to create a model. Okay. Like I said, there are several types of learning. So we have the semi-supervised learning or weak supervision. We have the ensemble learning. This is an example of a bootstrap aggregating. And what you're trying to do is, if you have different fruits, for example, you just make different sets of the fruits, and then you will feed those initial data sets to the algorithm and see how the algorithm separates or gives you a result. So we will find, for example, that one algorithm told us we're handling like an apple, and other two algorithms, the same algorithm with different initial data, came out with a grape result. And then we take the average by voting. So two of the algorithms for different initial data came up with the answer of grapes, and one of them came out with the answer of apple. So we will take the answer to be a grape. Okay, so that's bagging. So you just make an ensemble of different algorithms. Every algorithm has a result, and then you take voting. So two of them coincide that this should be a grape, and only one of them said that it was an apple. So that's bagging or bootstrap aggregating. Another one is, let's say you have an initial data set, and then you start doing some decisions, create a new set of data, and you create another tree, and then you continue doing all the cases until you get a good result. That is called boosting. Voting, I just mentioned, you have initial data, the same initial data for different algorithms. So what we will find is that there's no unique algorithm to solve something. So what we can do is just select a strategy of using 3 different algorithms and see what is the outcome of each algorithm, and then take a voting decision. And then we will take the answer that most of the algorithms voted on. So this is called stacking. So it's a very frequent way of solving a problem. And also every algorithm sees different structure in your data, different properties in your data. And that's why it's a good strategy to involve more than one algorithm. And by different structures, what I mean, for example, let's say you have a spreadsheet of different um, metrics, biometrics of people, and you will have a variable or a column that has the height, another one for the weight, another one for the gender, another column for probably some morbidity of the patient. And then every algorithm probably will see different. Like for one algorithm, maybe the height and the weight is more important than the age. Another algorithm may see that the age is more important than the weight, etc. So that's why you need to combine different algorithms in order to get the result. This is the dimensionality reduction. So we just mentioned what was the principal component analysis, but also we have the linear discriminant analysis. There's a t-distributed stochastic neighbor embedding. So these are different ways of reducing the dimensions of your problem. If you have a data set with 15 variables, maybe you can describe a similar problem with only nine dimensions. And these nine dimensions, I'm not saying that you just drop 6 columns from your data set. No, you will combine your 15 columns in order to have new 9 columns. So these are new uh, you will have a new space with lower dimensions, but this space is generated by a combination of your previous 15 dimensions. Then we have the NLP, or natural language processing, which is now very popular with all these large language models that we use and we see, for example, ChatGPT. So we need to train those models using text, and the text somehow is transformed into some language space, and then your algorithm will try, depending on the frequency of use of specific combination of words, it will try to guess the next word. So if my algorithm say my name is, and then it will try to see all the statistics and see what is the most popular name to predict what will be the next word. The same thing happens with the images. So we have computer vision algorithms. We see, for example, all these autonomous vehicles or taxis, driverless taxis. They are just processing the images from different cameras and sensors, and they will try to set up a path or a route that is free of any obstacles. So that's computer vision. Speech recognition algorithms. Well, there are many systems where you talk and it will just transform your speech into text, and vice versa. And then you'll find all recommendation systems. Whenever you log in into Amazon, they will tell you, well, people who have bought this thing also bought this other thing, and they will try to sell you something. So, or it will tell you this product has been bought 100 times yesterday, and this one nobody's buying. So it's recommendation systems. Also, it's machine learning. If we're going to be working with Python, Python is a general programming language. How many of you have heard of Python or have used Python or have never used Python? Maybe you have used R, right? Okay. So no worries. So in Python, there is a library. And by a library, I mean a collection of functions and procedures that can help you how to solve a problem. And this library is called Scikit-Learn, and we have more or less a it's not very clear, but more or less we have like a path for selecting the type of algorithm. Okay, so we are here to start, and then if we have less than 50 data points, then we have to do something else. If we have more than 50 samples, then we continue. And then if the, oh, sorry, let me find it again. Okay, so if we're going to predict a category, that means, for example, let's say we have a data set that, for example, the customers that go to a specific restaurant, and we have the time they went to the restaurant, if they went for a breakfast, lunch, or dinner, and then if the person smoked or not, we had information about the gender. So can we predict? And also we have how much they spent in the restaurant and how much they gave for a tip. So I can take that data and I say, okay, so I want to predict a category. So my data will be labeled. So for example, some of the customers have labeled they smoke or they don't smoke. Then what I can try to do is create a model And then from that model, if I have had less than 100,000 data, then I can use a linear singular value composition. And if that doesn't work, then I can do nearest neighbors, or I can do naive Bayes in order to predict, for example, by knowing the time of the time of the dinner, breakfast, or lunch, and knowing how much did it spend, how much did the person gave for a tip, can I predict if it's a smoker or not? So I have some label data that I use to train my model, and then once I have my model trained, then I can input incomplete data and try to predict the type of the new data, where does it classify or not. So that's like classification. If I don't have my data labeled, and then if I have the number of categories known, let's say you have a data set that describes 3 species of penguins, and these penguins are categorized by species, by island where they live, and you have all the different metrics like weight, height, peak length, flipper length, etc. Then you continue, and then if you have less than 10,000 samples, then you can use k-means to classify the 3 species of penguins. Or if that doesn't work, we can use spectral clustering or this other algorithm, GMM. If I have more than 10,000 samples, then I have to do this mini batch k-means. So it's more or less like a cheat sheet how to use different algorithms that you can encounter in Scikit-Learn. Okay, so in case you want to do a regression, you have a sample set, a data set, and then they don't have any, you're not going to predict a category, you're going to predict a quantity. So, and you have less than 100,000 samples. Let's say you want to predict how much time does it take for traveling from your home to the university. And then you can use probably lasso or elastic net or some other if this doesn't work. Okay, so more or less it's just a simple map, and the important thing is that Scikit-Learn will have all these algorithms and others in order to test. And the good thing about all the open source software, which is the case for Python. So Python is an open source software. You will find plenty of documentation and plenty of communities in the internet that can help you solve some problem. So in our case of the Scikit-Learn library, you will find, let me open this. So this is the Scikit-Learn library. And these are the types of problems or tasks you can solve. So for example, we can do classification. These are the types of applications. These are the algorithms. For if you're doing regression, you want to predict a continuous value, and some applications like drag response, stock prices, and these are the algorithms. The same thing with clustering when you're trying to group similar objects, or dimensionality reduction when you're trying to reduce the number of variables, or comparing model selection, comparing and validating and tuning your models, and preprocessing for feature extraction and normalization. The good thing that I said is that the documentation is there, and then when you go inside every section, you will find examples how to use, for example, ordinary least squares, It will come up with the explanation how to use it. It will propose segments of code or pieces of code of how to use this algorithm. And then so every time we'll have examples, and if there is an example included, you will have the snippets of code in order that you can try to implement this algorithm for yourself. So the best strategy is to find something that you want to do, find an example, and then adapt this example to your case. And you don't have to know everything about Python. What we need to know is how to read our Python code, and basically is similar to English. So we just need to know what each segment of code is doing in order to replicate and then adapt it to our case. And for example, I don't need to know anything about how to make a plot or a visualization. So I just take the code as is. I only need to know to change it into my data in order to get something very fast and quick. So those will be the advantages of using open source code like Python, and in our case, the using Scikit-Learn for doing machine learning. In our case. Okay. So do you have any questions up to this point? Okay. Okay. So in the next number of sessions, we will start seeing the different groups of algorithms in detail, and also provide you with different examples in order that at some point, if you need something to do something similar or analogous, then you can use the codes that are going to be provided. And then we have different topics, references that you can read on your own. And for example, we have these online resources. Let me open them. And it's a good collection of different, these are digital books which are available. So if you want to learn about machine learning, you just select the machine learning. And then below you will find books on classical machine learning. And everything is online, digital. So it's there. If you want to learn about Bayesian modeling, you find a book, okay? And you can read what is Bayesian inference modeling, etc. So it's a very good resource collection of sources. Also, you can find examples of different courses on machine learning. This is the one by Andrew and G on Stanford. This is from UC Berkeley. And then in the next, after this talk, we have the deep learning workshop. Also, you will find more learning resources on deep learning. So, so for example, you will find all the different resources that you can expand the topics that we are going to be doing here in the workshops. Okay. So we are just doing the part of classical machine learning. And then the next workshop is on deep learning. And with deep learning, we will be talking about neural networks, all these encoders, autoencoders, and even perceptrons, and how is it used for different applications like in vision or text, etc. Question? Right. So that's what I have. If you have any questions, if not, maybe we can transition to the next workshop in a couple of minutes. Okay.